Hello, thank you for joining us today. Please mute yourselves before our webinar begins. Thank you. Hello, welcome to our webinar on Introduction to Quantum Physics. I'm Yuzu, a rising senior from Great Neck South High School, New York State. I'm also the founder of the International Student Astronomy Organization, ISAO. We're a global community of high school students passionate about exploring the universe. And our mission is to raise astronomy awareness and prepare middle and high school students worldwide by providing knowledge for astronomy research, opportunities, and global collaborations. I will be your moderator for this webinar. Our invited speaker today is Xingzhi Li, a rising junior at Great Neck South High School. Xingzi's passion for astrophysics began with a curiosity about the fundamental building blocks of the universe, which soon led him to explore quantum physics. Academically, he is preparing to take AP Physics 1 and pre-calculus honors, and he has already completed advanced courses including Algebra 2 honors in AP Computer Science. As an active member of his school's robotics team, Xingzhi specializes in coding and problem solving. Beyond academics, he is also a decorated track athlete, having won multiple awards such as the SMR and 4x400 at Don Scott. And he has been recognized with the Gold Presidential Award for his dedication to volunteering. Hi, Xingzi. Thank you so much for being here with us today. Would you please elaborate on your journey with astrophysics?
Hello. Okay. For astrophysics, we just don't really talk about astronomy part, but so I was like really curious about like physics for about like really chemistry. It was like the chemistry classes that got me curious about physics. And then I was like wondering like why like it is happening and like well like you see like my chemistry teacher like really is really talking about chemistry. So I just started like researching on my own. And research, I mean like watching YouTube videos. And yeah.
Thank you so much, Xingzi. Xingzi will talk about the introduction to quantum physics. This talk will trace the fundamental forces of the universe, strong nuclear forces, color chromodynamics, and more. This event will also be recorded and made available on YouTube for future reference. Xingzi, would you please share your screen?
Okay,
Okay,
okay.
I'll
Just
give it to you.
uh-huh. Okay. Alright, so I tested this exactly 1 minute before. Should work fantastic. So I just go here. We could just press this button. Okay, everybody can see?
Yep.
Yeah?
Yeah, we can see it. Perfect.
Okay, so we're gonna basically spend like 30 minutes talking about introduction to quantum physics for two people, but that's fine. Let's start with the hook. So, have you guys, like been in chemistry class and just look at particles before, like an atom, and wondered, hey, I learned that like electromagnetism. So what, like how does the nucleus stay together? Or like, hey, like how does like beta decay truly works? And maybe like the teacher be like, hey, little Timmy, if you don't like stop asking questions, we ain't finishing the course. And she's probably right. So therefore, there's a lot of unanswered questions and a lot more intricate details about quantum physics that haven't really been discussed in school. And today, we're going to change that. We're going to try to learn the four fundamental forces besides gravity. Don't ignore that. And the reading of the elementary particles of the diagram. Hopefully that happens. So just a brief refresher on the fundamental forces. Like the strong nuclear force is basically like the force that's holding up the nucleus. Electromagnetism is like foundation entirety of chemistry basically is how like protons like likes repel each other and like the opposites like a proton and electron like attract. Gravity for the quantum field we don't really talk about gravity because it's very inefficient, well, like insignificant. So that's probably ignore that. And finally, weak nuclear force. That's how beta decay and how like neutrinos happens, and basically just how like protons and like how atoms could actually change between different atoms, and there's varieties of atoms. Okay, now before we jump into the forces, we just look at the elementary table of particles real quick. So, for those who have like completely beginning to quantum physics, the protons and neutrons are actually not elementary particles. They actually make up of quarks. In this case, up quarks and down quarks. And the gist of this table is that each of the matter particles, because there's technically antimatter as well, but each of the matter has three generations of the particles, and they're basically like the same part. Like for example, the up quark and the chum quark are basically have the same charge and spin. The only difference is it's a mass, which is a lot more heavier than the chum quark is a lot more heavier than the up quark. And same as for the electrons, electron neutrinos, and muons, muon neutrinos, and tau. But basically, the gist is that the later generations and like the heavier the particles are, um, they are like they're much more rare and probably don't really need to get into them because it's really just like the up quark and down quark and electrons and like electron neutrinos, and of course is their counterparts that really gonna be making up like the entirety of the world. And then we also have some bosons. We'll get to all of them actually, so hopefully that's gonna we cut Higgs and we'll eventually go to Higgs. But let's just start with something quite basic, which is actually the quarks, which is like the building blocks of protons and neutrons. So, if you just quickly look at this, we'll quickly go through the mass, which is in mega electron volt, which means that it is very tiny, but it does have mass, and it's not nearly zero. The charge. So the interesting thing about a quark is that the charge is actually um in fractions. So yeah, that's that's probably why it's very difficult to do a lot of math here. And then the spin is it's like a characteristic. It's just for the sake of simplicity, it's just gonna ignore that spin part. Okay, now just a quick rundown of some terms for quantum physics. So when it says a baryon, like when any object is filled with a baryon, it means it's made up of three quarks. Okay, and when I say like a meson, it means it's made up of two quarks. And remember, quarks could have like antimatter, so it will be antiquarks. But yeah, so that's just some basic definition. And protons and neutrons, the ones in the nucleus, make up of baryons. So that means they have three quarks within. We'll actually look into them right now. So protons and neutrons, as you might have remembered before, that an up quark has a charge of uh, two-thirds, and then the down quark has the charge of negative one-third. So a proton, with some quick math, will have two up quarks and one down quark, and then a neutron will be having an up quark and two down quarks. And those are just really the main difference between a proton and neutron. And you might notice the colors here, and we'll quickly get into the first fundamental force, which is the strong nuclear force. Okay, so before we really delve into this, I kind of lied. We need to go to color chromodynamics first. And we'll introduce you to the first force carrier, which is a gluon. Now, you might notice something strange. Hold up, it doesn't have any mass, and indeed it doesn't have any mass, nor does it have any charge. But it will carry colors. Now, um, color charge is quote unquote color charge because, well, actually the quarks can't have colors, they're too small for that. Is sort of like an arbitrary value given by the physicists. And you might look, each quark will have a difference of a red, green, or blue charge if it's a matter quark. And you might remember something in art school that if you combine red, green, and blue, it will make white. You know what? That is correct. And then you may remember that these antiquarks were the ones that form a meson would have, let's just, for example, in this case, red and anti-red. Well, you don't need to be smart enough to guess that if you combine red with anti-red, it will also make white. So the thing about color charts to really understand and to understand the strong force is that no matter how you put it, it needs to be white. Okay? Like no matter how you mix up match the color, it has to be white in total. And this will make a lot more sense if we continue on because this is how actually um, the protons and neutrons stay together. Okay, so this is the actual ways of color chromodynamics. Okay, so the gluons will be carrying two colors. Um, one color, one like actual color and one anti-color. And all it has to do, since a regular proton or neutron will have red, blue, or green because it will make white. So the gluon will be carrying like red, for example, and maybe an anti-blue, and will quickly between all three of them at a very fast speed. In fact, in this case, you can see that it's sort of like a flux tube, and that's actually it's called. And it will exchange the color so fast that it will actually bond these three quarks together. And once these three bonded quarks together, it is one of the strongest forces in the universe. Actually, it is the strongest force in the universe. And you might be asking, okay, then, but that does it mean that I can never break a quark up on its own? The answer is actually yes, you can't never see a quark on its own, but what happens if you infuse so much energy to try to break apart a quark? And this is specialty about the color charge and why it is so strong and how some specialty traits of the quarks is that if you actually infuse a lot of energies into a quark, as you see here, um, since with just Einstein's equation that the energy is like equals mass times constant of life squared, you will actually see that if you invest enough energy into in this case it will be a meson because it has two quarks, you will actually find that the energy used to separate these two will be converted into the pairs of the other quarks. So like the energy itself that is used to separate the quarks will be suddenly converted into its matching opposites. So suddenly it's like mitosis. You have two quarks now if you try to pull apart. And that's some specialty of quarks. And this is how the quarks, the protons and the neutrons themselves stays, you know, like protons and neutrons and why they're so like stable and hard to break apart. But how about the nucleus, right? Like the nucleus is full of protons and neutrons. And last time I checked, I don't remember there being, any way for them to not repulse each other. Well, that's where the residual strong force came in. Okay, this is what like the meson really interacts. Okay, this is a Feynman diagram. It is sort of like it's like the only difference between a regular diagram is like the time is upwards and like there's a bunch of lines and just like it's actually quite intuitive to see. Just don't worry about like too much of the finer details of this part. Okay, so as you can see in final Feynman diagram, it's actually these mesons, or more likely in this case, the most common type of meson, which is a pion that is actually created during the strong color chromodynamic phase of the strong nuclear force. And with the creation of the mesons, it is easily able to convert in this sense to another pair of color chromodynamics and exchange to, in this case, a neutron and subsequently converting it to a proton. So what you can imagine is that the strong nuclear force don't create new protons or neutrons. However, it just switches around all the protons and neutrons together since it is constantly swapping pions. So you could imagine that each proton and neutron is like within their own selves, color confinement with like their sweet colors like red, green, and blue keep swapping around. And then without like outside of it, with like all the protons and neutrons, they're also swapping the mesons, which is a quark and anti-quark pair that is also constantly switching the protons and neutrons into different types because it annihilates and creates different types of up and down quarks in combinations. But in general, it will make sure they will always conserve the number of protons and the number of neutrons. But that's actually the way why the strong nuclear force is able to overcome electromagnetism and to be able to stay together, hold the nucleus together. Now, there's one thing about the strong force to mention. The strong force is the range is very short. In fact, the only way the strong force actually act is by um, they actually exchanging virtual pions, but it's actually it can only exchange between its neighbors. And that's why as the atom gets larger nucleus, uh, proportional, like disproportional amount of neutrons is needed. Okay, so that's the strong force. That's actually probably the hardest part of force to understand. But if you take some time, maybe do a little bit of looking at your own, you probably can understand it. Now, let's go to the weak nuclear force. Okay. Before we go to the weak nuclear force, we need to quickly look at chirality. And for people taking chemistry might know what chirality is, but basically the elementary particles have a left-handed side of particles and right-handed side of particles. Now, you might be asking, why haven't you bring this up before? Shouldn't this be, sort of actually a very important to know? And the answer is the only force that actually differentiate between chiralities and actual chirality is a weak nuclear force. And the weak nuclear force can only interact with matter from the left-handed side of the chirality and antimatter from the right-handed side of chirality. Chirality is determined by spin, but actually the only time I mentioned it here, but like just know that weak force is a bit strange in case of chirality, and that's the thing. But actual weak force. Now we encounter two more particles. The first is the W boson. Now it actually does have mass and it does have charge. And the W boson, people who take in chemistry might be remembering, oh hey look, the W boson is to do with the beta decays and says, wow, I remember beta decay in my chemistry class. It's just when a neutron transforms to a proton or a proton transforms to a neutron. And what the school doesn't really teach on beta decays is that once you beta decay happens and like, maybe like this virtual W boson, whenever I refer to virtual particles, it means that the particles is like actually like, too fast to actually detect, and then we assume that it's there, but you can't really see it. So that's what a virtual particle is. But it also emits, let's just say beta plus decay, a positron, but also a neutrino. And this is where we get in your third sort of element to talk about, which is a neutrino. The neutrino doesn't have charge, it does have spin, and it does have mass despite it being so small. So neutrinos are very small. It does have mass, so it's probably like passing through most objects and doesn't really interact with anything. And the weak force with the W boson at this force carrier is how actually radioactive decay can even happen within nucleus, and it does emit neutrinos as a part of that radioactive decay. Whether it is like an anti-neutrino in the case of beta minus decay, or a positive neutrino in case of beta plus decay. Okay, now the Z boson. The Z boson is the second force carrier for the weak force. It is a bit cooked in the sense that it kind of interacts with neutrinos and interacts with electrons. It also interacts in this example with like the tau and with the quark. So it just basically also decays in particles. Just like the three examples I gave here, just remember the Z boson exist. It doesn't have a charge, but it's pretty massive, and it is how neutrinos interact with stuff and how other people interact stuff. But usually sending a virtual Z boson. So we're actually pretty fast and pretty good on time. So let's go to the third fundamental force, electromagnetism. Okay, now, but no, electromagnetism, it's really about photons. And photons is what the sun is made of. And the photons doesn't have mass nor charge. And we'll get through wave particle duality where the photons is both a wave and a particle. It's really depending on if the photons feeling it that day. So that we'll get to it later on. But important thing is Coulomb's law. So about the Coulomb's law, it is basically how particles really uh interact, and also it shows that the range of electromagnetism is actually pretty big compared to the strong and weak nuclear forces, as both of them is pretty small. And the equation is actually very similar to the gravity's equation, because they do quite act as gravity. And the final reason why the electromagnetism is pretty important is that it is actually the exchange of the virtual photons that help propel the the electromagnetism and the repulsions. So in the case of this Feynman diagram, with the time is upwards, the protons will meet together, but with the exchange of virtual photon, they will actually be repelled against each other because of electromagnetism, and that's pretty neat in my opinion. Now we're gonna quickly brush on quantum electrodynamics because this is a really subject on electromagnetism, and it will feel it would be like a disservice to it if I don't brought this up. But the three examples I brought up here is some of the biggest discoveries of quantum electrodynamic. The first one is confidence scattering, but with a bunch of like cool Feynman diagrams to show for you. But it's just um the very simple case of electrons. Well, not actually not electrons. That's a mistake. Photons acting as particles. So not only as acting as waves, like electromagnetic waves, that most scientists thought, but also acting as particles. Now we have the theory of antimatter. Now that's a pretty neat one in my opinion because it's just really math based. It's found by Feynman, in which case in the Feynman models, all particles will be going upwards in time because, well, we're moving upward in time, but the antiparticle is actually moving backwards in time. So Feynman thought of the theory as the antiparticles simply, our antimatters being simply the same matter except moving backwards in time, and therefore it has a different, like the positive with the opposite property of the charge of a regular matter. That's pretty cool and neat. We don't really have any tests for that yet, but that's just a cool mathematical theory. And finally, we're going to talk about a bit of electron position annihilation with QED. So when matter and antimatter meet, they destroy into each other and they produce photons. In this case, most likely it will be two photons that's very heavily energized. Now, this is a bit of a side tangent, but basically, some people might see this and say, hey, I remember in middle school that my teacher says the conservation of mass must be preserved. And I remember, if I'm not wrong, that electrons does indeed have mass. However, he literally said on last set ago that photons doesn't have any mass. So where did the mass go? Okay, now the answer to that question is actually that the mass itself, uh, it is sort of a lie. So there's really nothing considered as mass. Now, there is a thing called resting energy. That's a cool fancy way of saying of an object at rest. And that is what we define as mass. Um, but you might have heard that it's just energy, and it's all because of the Einstein's pretty big equation that he found, E equals mc squared. That the technically the object who is moving faster will have bigger, more mass, but it just means it has more energy. So that means the photons, yes, it does not have any resting mass, when the positron electron get destroyed, but the mass that the electron positron have is actually converted into simply kinetic mass or kinetic energy, which just means it's pretty fast with these photons. Okay. Okay, so we quickly go and touch on gravity. Okay, so you see the reason why gravity doesn't really exist in quantum mechanics is because gravity really deals with mass, and since the mass is so small, it gets overpowered way too easily by electromagnetism, strong force, and weak nuclear force. So there's some cool theories like matter going space-time time dilation, and everyone's trying to speed of light, but that's usually for the astronomy side of physics and when deal with larger objects. For the sake of simplicity and not cramming people too much information, just gonna exist that like the theory of relativity is out there, and the current day physicists predicted that graviton should be a particle, like like the very force of gravity should be an elementary particle. It's current day, it is we still didn't find it, but there's a prediction of it. Okay. And now we go move on to the Higgs field, which is like the uncle at the Thanksgiving dinner who creates everything, but you don't really want to interact it. So now you might look at elementary particle and think, oh, wow, it has mass. And how would it have mass? And the answer is with the Higgs field. So the Higgs field has a vacuum expectation value, in this case, 246 gigaelectron volts. And that means that even at an absolute vacuum, the Higgs field still have something like some mass. And that's the reason how the Higgs field is actually able to give mass to all of the other elementary particles. Okay. Now, how does a Higgs field give particles, give mass to the particles? It's sort of like this. The Higgs field is everywhere, and is everywhere in the universe. Same as the electron field, the quark field, and the neutrino field. Now, whenever an object, let's just say in the electron field, is disturbed or displaced, there will be an electron. That electron at purely on the electron field on itself, it doesn't have um, any mass. Therefore, it could go at the speed of light. However, it's very unstable and will quickly be neutralized. Now, when the electron interacts and couples, and that's the physics term, couples with the Higgs field, the Higgs field actually grant the electron mass so that yes, the electron can move at the speed of light, but the electron is actually more stable and could actually exist as a particle. Now there's one so that's really how the Higgs field works, but there's now one funny thing about all of this math stuff. So the quarks and um the quarks that make up of like a proton, which is the mass of the given by the Higgs field only makes up 1% of the total mass of the proton. And you may be wondering, okay, like how are we making up these extra 99% of mass? And turns out the extra 99% of the mass from the protons and neutrons came from, if you could guess it, then probably should be here. You should probably be here instead of not me. From the gluons, and the color chromodynamic that is happening within the protons and neutrons, and it's actually the energy. It's because of the energy that the gluons carries between the colors and of everything, and of the uh quarks exchanging colors. That is the reason that creates the mass of the proton. So technically, a human body is just 1% of actual mass. The rest is just 99% just energy. That's a cool thought for you. Okay, let's just give a quick review because that's a lot of stuff we just talked about. So we just gonna go back here to the up. So there's three generations of particles. With up down, the difference between the charges, the electrons is also fundamental particle. The neutrinos are nearly massless. They do have mass though, and they rarely interact with anything. The uh the gluon is the force carrier for the strong nuclear force. It's how the atoms stay together. With the nucleus stay together. The W and Z boson is for the weak nuclear force. Is how the radioactive decay happens and how neutrinos does stuff. The photons is for electromagnetism. It's how like the entire chemistry works. There's a gravity that is non-existent, but the gravity is also the fourth fundamental forces is everywhere with mass, and the Higgs is just a scalar force that's really and giving the mass to all the rest of the fundamental particles that have mass. Okay, so that's a quick review, and that's basically all of introduction to quantum physics. If you even get like maybe like 20% of what's happening, then you're probably good to go. And thanks for watching this presentation.
Okay. Xingzhi, thank you so much for your amazing presentation. We enjoyed it a lot. And also, we have some questions from my friends as well as in the chat. So let's move on to the Q&A part.